Okay, it's time to start. Today I will talk about flavor. So the flavor puzzle was one of the open questions in the list of open questions that we had last time on our road to beyond the standard model. The literature for today's lecture is listed in this slide. We will mainly use the first lecture notes by Josef Nier, which I really recommend you to read. There are also excellent lectures by Gino Isidori, which are actually videos recorded on the link that you can find on the slides. And then there are two written up lecture notes by Jura Zupan and Yuval Grossman, Philip Tanedo, which I also find quite useful if you want to get deeper into this field, flavor physics. So before starting, I would like to introduce some terminology which is used in this community. So flavor refers to copies of the gauge representation. So specifically in the context of the standard model, we think about the unbroken standard model gauge group, which is QCD cross QED. And there are four different types of representations of matter fields, of fermions, under the unbroken gauge group. These are up-type quarks, down-type quarks, charged leptons, and neutrinos. So there are these four types of different representations, and all of them come in three copies, in three flavors. Okay, first, second, and third generation. So flavor is a copy of the same gauge representation. Flavor universal or flavor blind means that doesn't distinguish between different flavors, and in particular, it means that it's proportional to a unit matrix in flavor space. Flavor number, when we talk about flavor number, we will talk whether it's conserved or violated. And flavor number is, if you have some interaction process, if you have some process, then you're counting number of particles of certain flavor minus the number of n-type particles of the same flavor. So n-type particles have a different, all the internal quantum numbers are flipped. So flavor violation has to do with whether the flavor number of the initial state is the same or different from the flavor number of the final state. If the two are different, then we talk about flavor changing or flavor violation. There are two types of interesting flavor violation. The first one has to do with the neutral currents, flavor changing neutral currents, or FCNC. These involve either up-type flavors or down-type flavors, but not both. And the second group are charge currents, so flavor changing charge currents. They involved both types of both up types and down types. For example, in the quark sector, it would be up type quarks and the down type quarks. In the lepton sector, it would be neutrinos and electrons. All right, so this is just some words that I will use in the following. So why is flavor physics interesting for beyond the standard model? I will give four arguments, which I think are quite compelling. The first one has to do with the indirect discovery. So flavor physics has a potential to discover new states, the existence of very heavy particles before they are directly observed in colliders. A historic example are charm and top quarks. Both charm and top quarks were the indication of their existence came before their discovery in flavor physics by measuring some flavor transitions precisely at low energies. Even more, if you assume standard model, you could measure the char mass and the top mass, so you can make a prediction where to look for it in colliders. And this is really how it happened historically. Today, flavor transitions are very sensitive to new physics, to potential new physics, and they could well be the first signs of new physics, even before high PT LHC, for instance. This is why it's very important to study flavor physics in the context of beyond the standard model. This closely related subject to flavor physics is CP violation, in particular CP violation in flavor changing processes. We know from cosmological evidence that we need new sources of CP violation. The baryogenesis, the asymmetry between matter and antimatter we observe in the universe cannot be explained in the standard model. In particular, CP violation present in the standard model is not enough. So we know this is a clear indication of the existence of BSM. Finally, the other 2 points have to do with the flavor itself. So the standard model flavor puzzle is an open question. When we look at the flavor parameters, for example, masses of quarks and leptons and mixing matrices, we see a very peculiar structure. And which certainly, so it looks like it has some hidden, so there is some underlying physics which should explain it. So it's a puzzle. I will talk about it a lot. And most likely it has a BSM explanation. So it's a road to BSM. And the fourth one, the final one, is the new physics flavor puzzle. So the point here is that we hope there is new physics at the TeV scale, tera electron volt scale. For example, from the Higgs hierarchy problem, we have a clear indication of the new scale. So if we don't want to allow tuning of the Higgs mass parameter, then new physics should not be far above the TeV. However, in flavor physics, we have measured certain transitions, flavor changing neutral current processes, in particular meson mixing and meson oscillations, neutral meson oscillations, which, however, exclude the existence of new physics to a very high scale if you assume order 1 couplings. So if there is new physics at the TeV scale and it has some kind of generic order 1 couplings, then we should have seen them long ago in flavor changing neutral current processes. This would be connected a bit to the first point. Such new physics we should have seen already. So the oscillations of B meson should have been different, for example. And this did not happen. Why this doesn't happen? This is the new physics flavor puzzle. Okay, so these are these 4 interesting things. And now I will go more into the flavor data. So PDG, particle data group, the big part of it is about flavor. So here there are a couple of transitions. These are decays of mesons. A B meson, which has a bottom quark inside, a kaon, which is a stranged meson, and D, which is charmed. So looking into flavor data, you can see some patterns. For example, there is lepton universality. In particular, the transition, if you look at the first 2, you would see that the rate going to muons versus electrons is the same, appears to be the same. So changing leptons doesn't make a difference. Another thing that you can see is when you compare neutral currents to charge currents, that neutral current transitions, flavor changing neutral currents, are extremely suppressed. Have a look, for example, B sub s to mu plus mu minus. The branching ratio is 10 to minus 9. So this is a transition of a B quark to a strange quark. Both B and strange have the same charge, minus 1/3. While, for example, look at the B to D, which is bottom to charm transition. This is a charge current. And that one is orders of magnitude higher branching ratios. So flavor changing neutral currents in the standard model are, I'm not talking, sorry, forget the standard model. Flavor changing neutral currents in nature, as we see them, as we measure them. So PDG is a collection of measurements. Appear to be way smaller than charge currents. Flavor changing charge current transitions. All right. Another interesting observation from data is that a decays between third and first generation, namely B to pi, which is a B quark to the first generation quark to up, B to up transition, has a branching ratio 10 to minus 5 compared to, let's say, B to charm. D quark is, D meson is charmed, B to charm transition, which is 10 to minus 2. So that there seems to be hierarchy between going from one generation to, from third generation to first is suppressed compared to third to second. All these measurements confirm the standard model of particle physics. So here you can see this, the CKM triangle, and you can see how different measurements, different measurements really agree with each other. However, the standard model cannot explain many features. For example, the generation hierarchy. Why it can parameterize it. There are enough parameters in the standard model to fit the data, but we don't understand why, for example, a transition of a third generation quark to the first one is much smaller than of a third generation quark to the second one. Okay. So the standard model is merely a parameterization of flavor. Okay. So let me go through the standard model and try to explain flavor in the standard model. This is going to be a little bit technical, but I will try to, if you have any questions, please interrupt at any point. So in the standard model, it's a gauge theory. It's SU3 color for QCD, SU2L for weak electroweak, and U1 hypercharge. So there are 5 representations, 5 different fermionic representations under the standard model gauge group. These are left-handed quarks, right-handed up quarks, right-handed down quarks, left-handed leptons, and right-handed charged leptons. So left-handed fields are doublets, right-handed fields are singlets. But so we have these 5 different representations. If we look at the kinetic term, this is the kinetic term of in the Lagrangian. You can see all these different 5 fermionic representations, which come in 3 copies. Each of them, it comes in 3 generations. And there is this covariant derivative which come along. So this part of the Lagrangian is flavor universal. Remember that this means that there is this in flavor space. So there is this delta ij Kronecker delta, or a unit matrix in flavor space. So this is flavor universal as well as CP conserving. Flavor and CP violation comes from the Yukawa Lagrangian. Okay, in the standard model, there is another potential source of CP violation, which we haven't, which is experimentally very small. The QCD theta term. If we neglect that, the flavor and CP violation in the standard model is entirely sitting in the Yukawa Lagrangian. So Yukawa Lagrangian is the interaction between two fermions and the Higgs field. So for instance, the first term gives masses to the down type quarks, the second term is for the up type quarks, and the last term is for the charged leptons. Neutrinos are massless in the renormalizable standard model with this field content. All right. So one thing that should be noted is that the kinetic Lagrangian has a large global symmetry. So if we switch off Yukawa Lagrangian, so we switch off the YU, YD, and YE, there is this big global symmetry, meaning that we can rotate the. So we have, if you pick, let's say, one representation in this kinetic term, let's say this one, Q. So I runs from 1 to 3. So we can do a unitary rotation. So we'll have a U, and this bar means U dagger. So we'll have U dagger U, and it's always going to be 1. So the term will be invariant under unitary rotation, U3. So we have 3 SU3s for the quark sector, 2 for the lepton sector, and each representation has a U1. So a UN can be written as SUN times U1. All right. So when we switch on Yukawas, so when Yukawas have some non-zero values, then we break the global symmetry. And in particular, we break it in a very specific way down to a baryon number and 2 individual lepton numbers for electron, muon, and tau. This is what happens in the standard model when we switch on the Yukawa couplings. In the next lecture, we will do a computation, parameter counting, where you will see more explicitly what's going on. These global symmetries are actually accidental. That means that we did not require them when we constructed the standard model. We did not put them in as a requirement. What we did, we set the gauge symmetry, we choose the field content, and we choose renormalizability because we discussed this last time, that at low energies only up to dimension 4 terms survive. Dimension 4 included, the other one die out because of the renormalization flow. So if you take these 3 conditions, then you get these global symmetries. This is why we call them accidental. You get out from the construction together with Lorentz, Poincare invariance set. So there are some things that we can already learn from this. For example, proton decay is forbidden. Proton cannot decay. Why? Because proton is the lightest particle which has a baryon number. Then there are no flavor changing neutral currents in the charged lepton. So there is no lepton flavor violation. Lepton flavor violation is forbidden by these 3 U1s for each lepton flavor. So you cannot have something like muon going to electron photon in the standard model. And also neutrinos are massless. We cannot write down we don't have a right-handed neutrino in our field content. We cannot write down the Majorana mass term at renormalizable level. So, but these accidental symmetries, from the point of view of beyond the standard model, are extremely fragile. Okay, it's super easy to break them. In fact, if you remember the standard model effective field theory, already at leading order, at dimension 5, you can write down a term which respects gauge symmetry and Lorentz symmetry, and it breaks the lepton numbers. So this is this Weinberg operator, L square phi square. That one breaks the lepton number, accidental symmetry, and generates Majorana mass term for the neutrino. Also, if you ask many people, we have already measured this operator in a sense. We have seen neutrino oscillations, so we know that neutrinos have mass. Now, this mass can be either Dirac or Majorana, and to many people, Majorana option is more compelling. Okay, at dimension 6, we can write this kind of operator with 3 quark fields and 1 lepton field. Again, consistent with basic symmetries, input symmetries like space-time and gauge symmetry. But this one violates baryon number and lepton number. And this one, for example, would lead to proton decay. And the scale inside is constrained to be more than 10 to 15 giga-electron volt. All right. So already from this symmetry discussion, we learn many things about we learn many things about how things work in the standard model. And these type of symmetry discussions are crucial also when going beyond the standard model. Let me now derive let me now see where is flavor violation in the standard model. So try to derive the interactions between matter and gauge bosons. So I will first, before doing electroweak symmetry breaking, fermions are massless. Okay, electroweak symmetry protects the masses for fermions. So we can do. I will start in a specific basis. So I can use this global symmetry to rotate fields, and while rotating fields, all the terms in the Lagrangian stay invariant, but the Yukawa term. And the Yukawa matrices change, going from one basis to another by rotating different fermionic fields. I can pick a basis in which down quark mass matrix is diagonal. Up quark Yukawa has a special form. It's a product of a unitary matrix and a diagonal matrix. And charged lepton Yukawa is diagonal. This comes from the singular value decomposition, a theorem in algebra, and it will become more clear next hour how it works. But for the moment, just take it for granted. I can do these rotations of fields and come to a basis in which I have these properties: diagonal down quark and charged lepton, and up quark having a special property, which is a product of a unitary times a diagonal matrix. In this basis, the mass eigenstate fields, so fields are rotating, and if you want to do phenomenology and calculations, for example, calculate S matrix elements, you would prefer to work in the mass eigenstate basis. You want to get to the field which is which is a creation of a particle with definite mass. Can create an annihilate particle of a definite mass. So the mass eigenstate fields, which are these small lowercase letter u, d, e, nu, l, they organize themselves in a doublet in this way. So in the left-handed quark doublet, we see the appearance of the same unitary matrix as before. Now you can check this. You can plug in QL into the Lagrangian below. For instance, let's take QL and plug it into the second term. Then let's take YU to have this special form, V dagger Y hat. Then you will see, you will have a V times V dagger, and this is 1 because V is a unitary matrix. In fact, V is the CKM mixing matrix. Okay, so after replacement, the Yukawa interactions become diagonal with the neutral component of the Higgs field. Okay, so when we do this and we plug in the Yukawa Lagrangian, the Yukawa interactions with the neutral component of the Higgs become diagonal. But we have to do the same replacement everywhere else in the standard model Lagrangian, in the kinetic term in particular. So the only place where this unitary matrix appears is in the interaction with the W boson. Okay? In particular, interactions of the photon and Z and the gluon are flavor blind. So the V does not enter in these interactions, and this delta ij index, delta ij, so it's proportional to the unit matrix in flavor space. Higgs interactions, on the other hand, are flavor diagonal, but flavor non-universal. So the Higgs interactions come from the Yukawa sector. And in the Yukawa sector, we have achieved a diagonal. We have now all the terms being diagonal. So that piece will give masses to fermions, but also the interaction to the Higgs. So the Higgs interaction will be proportional to the masses of the fermions. It will be diagonal, and it will be, so there is no flavor changing. So Higgs cannot change flavor between strange and bottom quark, for instance. But there is a violation of universality. And finally, the interaction of the W boson have the CKM matrix. So it can change flavor. This is flavor violating or flavor changing. So here I'm talking about, I'm staying in the unitary gauge of the standard model. So the only flavor violation in the unitary gauge is in the vertex of the W boson. Okay. And it is where the CKM matrix sits. All right. Let me do a very short excursion beyond the standard model. So the universality or blindness of photon and gluon interactions guaranteed by the unbroken symmetry. But the universality of Z interactions is accident of the standard model field content. So if you look at the Z Lagrangian, remember when we have to put, with the up fields, we have to put the CKM matrix. So we are putting for both fields. So there is V and V dagger. And the only reason why this is invariant is because there is one unit matrix in between, meaning that all the lowercase u come from the same representation of the standard model. So but this is just an accident of the standard model field content, and it's very easy to change when you go beyond the standard model. For example, one popular extension is to add a vector-like quark. In particular, top partners are motivated in many BSM scenarios, for example, composite Higgs. So if you add a vector-like, heavy vector-like quark, which is a weak singlet, so both left-handed and right-handed fields are in the same standard model representation. This means vector-like. Then the Yukawa Lagrangian changes, and when you have electroweak symmetry breaking, you will have a mixing between up and down, between up quarks, for instance. What does this mean for the Z coupling? Well, when you write down the matrix for the Z coupling, you will see that it's not proportional to 1 because you start with the different representations. And then when you do the flavor rotation, it will not stay 1. You will have flavor violation. So the fact in experiment, we see that the interactions are rather universal to a good degree. We can put limits, constrain such beyond the standard model scenarios. We can put stringent limits on vector-like quarks. For example, 1,2 element in this matrix is constrained by d meson mixing, for instance. And therefore, it's very stringent to be less than 10 to minus 4. Another example is about the Higgs interactions. We already said that in the standard model, they are diagonal, non-universal, proportional to fermion masses. But this prediction of the standard model is very easy to modify in the presence of new physics. So for example, if you add another Higgs doublet, so if you have 2 Higgs doublet model, then you can write down, you can double the number of terms in the Yukawa-Lagrangian, and you can have couplings of the Higgs boson, the one that we have observed, to be neither proportional to the mass matrix nor diagonal. Okay, in 2 Higgs doublet model, the couplings of the Higgs in general don't have to be proportional to the mass matrix, nor they are diagonal. So you can completely break the relation of the standard model. And 2 Higgs doublet model is not something exotic. It is something that you have naturally in supersymmetry, for example, in MSSM. This is really like vanilla beyond the standard model. So I gave these 2 simple examples only to remind you that about this fact of indirect discovery. These are only a few out of many BSM examples where flavor data plays a key role to constrain it. Move on to the second, to a different topic, which is the standard model flavor puzzle. So we have measured the flavor parameters in the experiment. These are the masses of the fermions, the CK mixing angle for the quark sector. And in the lepton sector, this would be masses of the charged leptons, and we also have some parameters of the neutrino in the neutrino sector. We haven't measured all of them. In the quark sector, we did a good measurements. And in particular, we got a very strange numbers. For example, look, this is the log scale here, masses of different quarks and charged leptons. So you see that the first, second, and third generation are hierarchical. The masses are hierarchical. And this is very strange. So imagine, so you have these Yukawa matrices, which are input parameters in the standard model. They are just free parameters. So now, to get the mass, you have to diagonalize this matrix. Now imagine if you throw in random numbers into Yukawa matrix, and you diagonalize. You would expect that masses of fermions are of the same order. You don't expect to see hierarchy of the eigenvalues in this. Well, why do we see the hierarchy of the eigenvalues of these matrices? That is a puzzle. In addition to that, the CKM matrix has a very special structure. It's actually very close to unit matrix. Remember, the standard model is just an arbitrary unitary matrix. We see that it's very close to the unit matrix. And then as you go off the diagonal, there seems to be a clear expansion parameter, this Cabibbo angle. So 1, 2 is Cabibbo angle, then 2, 3 is Cabibbo square, and 1, 3 is Cabibbo cubed. If you remember this generation hierarchy, for example, why B meson goes to, so the fact that B meson goes more often to D than to pion translates that measurement is the measurement of the CKM element. It translates onto this hierarchical structure. So why is this alignment between the rotation of the up left and down left? They seem to be the CKM matrix seems to be close to 1, and there is a well-defined expansion above from the diagonal. So this is not per se a problem of the standard model, because these parameters are input parameters and you fix them from the experiment. But their weird structure suggests that there might be new physics at short distances or high energies, which explains it, which explains this weird structure of the quark sector and charged leptons. In addition to this hierarchical structure of the quarks and charged leptons, neutrinos behave very differently. The structure of the neutrino seems to be anarchic. Apart from the smallness of the overall scale of neutrino mass, the mass, I mean, we don't see the mass hierarchy and the mixing parameters seem to be order 1. It's also true that we haven't, so far when we look at the neutrino flavors, we see it looks anarchic. And this just deepens the standard model flavor puzzle. So why quarks and charged leptons have this hierarchy while neutrinos are so anarchic? In the neutrino sector, we haven't measured all flavor parameters. We have measured 2 mass differences. We don't even know the absolute neutrino mass scale. We only know the mass differences, the 2 mass differences, and we know 3 mixing angles. We haven't seen any CP violating phase. So this is a big puzzle. Like why the standard model flavor puzzle is why these parameters are as they are. And to many people, this points to existence of beyond some extension of the standard model, which explains it.
Can you hear me? I have a question.
Yes, please.
How do we know which of the leptons belong to which generation?
So it's ordered by mass.
By mass, okay.
Yes.
So, but that would make this problem of the hierarchy a bit less severe, right?
Sorry, say it again.
That would make this problem of the hierarchy a bit less severe, right? So
why?
Now it looks that all the blue, you can't see my mouse, sorry. Now it looks, as you presented it, it's a puzzle that there's a mass hierarchy between the generations, but if the generations are partly associated by their mass, it's maybe not such a puzzle, right?
Right. So the puzzle is why. So you're saying that, let's say, within a generation they are roughly of the same order, but why is there difference between the generations? That is a puzzle.
Yeah.
I will take a few minutes just to go through just to show you one BSM which tries to explain which tries to address the flavor puzzle. So why would you like to address it? If you look at the gauge couplings and the Higgs self-coupling, these are the couplings these are non-flavor couplings. They come in the kinetic Lagrangian and in the Higgs potential. Okay, so these are some couplings from a different sector. They seem to be 1.1, 0.6. They're not super small. They are order 1, while flavor parameters are wild. Like electron Yukawa is 10 to -6, and then you have this. The only order 1 parameters are top Yukawa and Kobayashi-Masakawa phase, the CP phase in the. That's just a different way to look at this flavor puzzle. There are many models on the market how you can explain this. One very popular model is the so-called Froggatt-Nielsen model. So what Froggatt-Nielsen does is to postulate a presence of an additional symmetry, let's say a U1, which is approximate, meaning that it's broken. And in particular, it's broken in a well-defined way by, let's assume there is a small spurion epsilon, which has a charge under U1. Each standard model field has a charge. The word horizontal comes from the fact that we charge different generations differently, and vertical is associated with the SU2 gauge symmetry. So horizontal is associated with flavor symmetries. And then when you construct a Lagrangian, the rule is that you are invariant under U1H when you include the spurion and the fields. So what does this mean for the Yukawa coupling? So in the Yukawa coupling, you will have two fermions and you will have two fermions and the Higgs field. Okay, so you will put the so each of them have different charge, and then you have to insert a spurion to compensate for these charges. And this will give you a texture of the Yukawa matrix in terms of the spurion. And for example, this is one choice. So if you take charges to be 2, 1, 0 for the three generation of the Q, U, and E, then you get this texture. Okay. And when you diagonalize it, etc., you can realize the observed hierarchy in the charged leptons and quarks, and you can also you get also anarchy in the neutrino sector. So how do you complete the Froggatt-Nielsen? So what is a spurion? I mean, just the bookkeeping device. So what is it at the fundamental level? We can think about it as a web of some field. So imagine there is some scalar field, and they are called flavons. When they get a web, they break U1 symmetry. So you need to, so the epsilon will be the ratio of this web with respect to some heavy scale which generates these operators. Typically, you have some fermions which are generating these effective operators between the standard model fields, standard model Higgs, and the flavon fields. Explicit realizations of Froggatt-Nielsen do not look very beautiful. Okay. The standard model flavor puzzle is a hard problem, but it's very interesting. And yeah, I will stop here and maybe take, if there is a pressing question. Otherwise, we will go for a break. Before going to the calculations, to some calculations, I will finish these slides. In particular, I have to tell you about the new physics flavor problem. So in the previous lecture, we covered the aspect of flavor physics being very good in indirectly constraining new physics, and I gave two examples of how one can have flavor violation of the Z and Higgs couplings. We also covered the standard model flavor puzzle, and now we are on the new physics flavor problem. Unfortunately, I will not have time to discuss more about CP violation. Well, the new physics flavor problem has to do with the fact that we have measured certain rare transitions in the standard model. For example, the oscillations of a meson, neutral meson. For instance, here you can see a Feynman diagram in the standard model for a B0 oscillating into B0 bar. By measuring these oscillations, we can set very stringent constraints on new physics. For instance, consider a new physics which comes with dimension 6 operator, 4-quark operator. So these are leading new physics terms, excluding which preserve baryon and lepton number. Okay, so you can the fact that the observation is consistent with the standard model, you can set a very stringent constraints on the Wilson coefficients of these operators. And this table summarizes the constraints for different meson mixing. So we have at our disposal kaons, D mesons, B and B sub S meson. There are 4 systems. So you can put the constraints on all of these various operators. You can interpret them in 2 ways. One is if you assume that this coupling Z is 1, and you put a lower bound on the new physics scale. So you say that the couplings, the couplings which enter there are, okay, order 1. Let's see what is the limit on the scale. And then you get these huge limits. This is in TeV, in tera electron volt, which goes to hundreds or thousands or even more TeV. For CP violation, even yeah, they can be even worse. This one is 10 to 5 TeV. Okay, so that's one way how you can interpret these results. The new physics is far up in the sky. It's far away from to being reached by our collider, by LHC or FCC even. And the other option is to say, okay, new physics is at the TeV scale. So I fix lambda, I say it's TeV, and then see what is the limit on the coupling. And then you see that the couplings should be very small. So the second way to interpret this is to say that, okay, new physics is not far away, it's close, but the flavor structure is far from generic. So there are these 2 different ways how you can interpret the current data. So I very much prefer the second option, in particular, weird flavor structure for new physics. And there are a couple of arguments why this. So first, standard model has a weird flavor structure. It's far from generic. Why would we expect new physics to have a completely anarchic flavor structure? And second, we have indications that the scale of new physics is not far away from TeV. For example, from the Higgs hierarchy problem. That's what we are going to talk about it next time. Of course, this could be just a prejudice. So the new physics flavor problem is about that. If we believe that there is new physics at the TeV scale, why does it have such a? Why we haven't seen anything, and why it has such a peculiar structure? One way to explain the new physics flavor problem, the absence of flavor changing neutral currents beyond the standard model. We have only those that are predicted by the standard model, but some new flavor changing neutral currents is the so-called idea of minimal flavor violation. So the idea is to assume that even when you have a BSM, so you extend the standard model and you go to BSM, you assume that the only source of flavor violation are the existing Yukawa couplings. It turns out that this principle can protect, so it can guarantee that in low energy flavor changing processes, you only have small deviations from the standard model, even though you have a TeV scale new physics. So formally, you think about Yukawas as flavor breaking spurions. And if you do some power counting and you put them in these operators, in the third column, you can see the prediction that comes from MFV and MFV and okay, this Jim and Jim I didn't talk about. For a TeV scale new physics, you can see that the couplings are small and that they can satisfy, in most cases, they can satisfy the current constraints. Minimal flavor violation is predicted in some new physics. For example, if you have a gauge mediation in supersymmetry, at low energies, you get this minimal flavor violations setup. What's the purpose of minimal flavor violation? It is to have new physics at the TV scale consistent with flavor bounds. On this plot, you can see the bounds from different flavor observables on the scale. If you assume generic couplings, so you can see that they go to really, really high scale. For example, the dipole moment of the electron, which is a CP violating observable, can probe scales which are 10 to 7 TeV. But if you assume minimal flavor violation, then you get these hedge field constraints that they are much lower for that scale, and the scale is not far away from the TeV. Maybe in this case is about 10, 20 TeV, I said, or the neutral. But you see the mesons go down, yeah. So that is the power of minimal flavor violation. Anyway, generic lesson is if you want to have new physics not far away from the TeV scale, then it should have a funny flavor structure. In particular, should be close to minimal flavor violation. Minimal flavor violation is not the only option. There are other options to protect from these dangerous FCNCs. Okay, we say dangerous FCNC. For example, U2 flavor symmetries. And recently there was a very interesting paper which does MFV and U2 counting in the full SMEF at dimension 6 level. So they take, in standard model EFT, there are, if you include flavor indices, there are 2,499 different operators. And then you can impose flavor symmetries. For example, if you MFV, saying that you are just putting in the Yukawa couplings and making every term invariant under, formally invariant under the flavor symmetry group, and then you do the counting. You drastically reduce the number of operators, and yeah, it's a very nice. I don't have time to talk about it, but it's a very nice read if you have time to look at it. All right. Do you have any questions about the slides? Because I will switch to my notes. Okay, so we have something like more than half an hour. So I will try to do 2 exercises. The first one will be about the parameter counting of how many parameters we have in a theory, flavor parameters, 2 different methods. And the second one will be about some diagonalization procedure for vector-like quarks. I chose these exercises just to show you some common manipulations you do when you regarding to this flavor physics for model building for BSM. Okay. So let's do the parameter counting in the lepton sector, and first assume that neutrinos are Dirac. So in particular, we have a right-handed neutrino. Okay, so we have a right-handed neutrino. So there is a left-handed lepton doublet, there is a right-handed electron, and a right-handed neutrino. All right, so the Lagrangian, the Yukawa Lagrangian is given by this line. So there is the first piece, which is the interaction of the right-handed electron, and YE is the Yukawa coupling. I, J are flavor indices which go from 1 to 3. And the second term is the Yukawa coupling for the neutrino. Remember, we don't have this in the standard model from previous lecture. So this is an extension of the standard model by adding a right-handed neutrino. Okay, so now the Higgs gets a VEV, so the neutral component, so we have a electroweak symmetry breaking. The neutral component gets a VEV, and this Lagrangian generates the mass term. So there will be the mass matrix for electrons and neutrinos, and they are in general complex 3 by 3 matrices, both of them. Okay. So now we will use the singular value decomposition. So it's a theorem which says that you can generalize an arbitrarily complex matrix by a biunitary transformation. So you have a unitary transformation you apply it from left and right, and you will get a diagonal matrix. And furthermore, a diagonal matrix which has real non-negative entries. Okay? So like masses are real and non-negative. Okay, so let's write down the fields after electroweak symmetry breaking. So we have we expand SU2 indices. So we have lowercase EL, ER, nu L, and nu R. These are just the kinetic terms of the free Lagrangian. So at that level, when we broke the electroweak symmetry, we can perform 4 unitary rotations in our Lagrangian. We can do I will call them U and UEL, UER, U nu L, U nu L for electrons and for neutrinos. Okay, so let's do it. So we are going to rotate electrons and neutrinos with this, use the singular value decomposition. And in the Yukawa Lagrangian, we will get 2 diagonal matrices. So in particular, in these matrices, we will have 3 charged lepton masses and 3 neutrino masses. Okay? So these are 6 parameters, 3 masses for the leptons and 3 for neutrinos. Now, once you do this rotation in the Yukawa sector, you have to do it everywhere else in the standard model Lagrangian. And it cancels, as we saw on the previous, as we discussed. So for example, in the interactions of the Z boson, they would cancel because you always couple the fields of the same chirality. So it means you are using the same rotation. There is an identity matrix in the flavor space. It's because it's blind, the blind interaction, and then U dagger U will be 1. The only place where it doesn't cancel is in the interaction of the W. So why? Because W couples different representations under the broken gauge symmetry, under QCD and QED. In particular, W couples neutrinos and electrons, and also it couples up quarks and down quarks. So when you do the rotation, you will have, as you can see here, you will have a neutrino left-handed rotation and the electron. And this is called the PMNS matrix, VPMNS. It's also a unitary matrix. The product of 2 unitary matrices is a unitary matrix. So, a unitary matrix has 6 parameters, 3 dimensions. So 3 times 3 unitary matrix has 6 parameters. 3 of them are real and 6 imaginary. So you can think of this as so the real degrees of freedom, you can think of orthogonal matrix in 3 dimensions, and you can do 3 angles, so 3 rotation angles. And there is additional 6 phases. So you have 3 angles and 6 phases in a unitary matrix. However, not all of these phases are physical in this specific example. There is still freedom to do some phase rotations. For example, look at this Yukawa Lagrangian. We can do the phase rotation for each. So we can do the phase rotation for each flavor independently. For example, electron flavor can have its own phase rotation, etc. The same for neutrinos. By doing these phase rotations, we will not change the mass term, okay? Or anything else except this, right, so you can see here that the mass term doesn't change because you have a dagger, and so the product of the two is 1. It doesn't change. So you can do this phase rotation, and the only place where you have impact is the interaction of the W neutrino electron. So here you can have an impact if you do these phase rotations for each flavor independently. You can use 5 phases. The common phase, which is the lepton number, meaning that you change muon, electron, tau, and the corresponding neutrino flavors with that phase. That's the symmetry of the Lagrangian. So lepton number is the full symmetry. Also, the term with the W interaction will not change. So if you have a common phase for all of them, also this term cannot be changed. It means that is a symmetry of this Lagrangian. So you can use 5 phases to change the PMNS matrix, to change the basis of it. What does it mean? So you can go to a basis where it only has 1 phase. So you can remove, in general, a unitary matrix has 6 phases, but you can go to a basis where you have only 1 phase. It means the other ones are not physical. So in the end, CKM can be written as 3 angles and 1 phase. This 1 phase is the Kobayashi-Masakawa phase, and these angles are these parameters of the CKM. So the counting here is this: if neutrino is Dirac, is the same as for the quarks. That was sort of a brute force way to count the number of parameters. So we have 3 masses for charged leptons, 3 masses for neutrinos, and 3 angles in the PMNS matrix and 1 phase in the PMNS matrix. So if neutrino is Dirac, we have these 12 real and 1 imaginary parameter. Sorry, 9 real and 1 imaginary parameter. There is another way to count parameters, which is more handy if you have, for example, a BSM model, rather than this brute force one, and it is to use a group theory approach. So to utilize these global symmetries. So remember, if we remove the Yukawa interactions, we have a global symmetry, which is the product of 3 U3s, U3L, U3R, and U3Nu. This global symmetry is broken down to lepton number, U1L. If we switch on, it's broken down to lepton number if we switch on Yukawas. When looking at this Yukawa E and Yukawa Nu, there are they are 3 by 3 complex matrices. So in general, they have 9 real and 9 imaginary parameters each. Okay, so let's look at the breaking structure of the flavor group. So we have U3 cubed, which is break to U1 lepton number. How many broken generators do we have here? So we have, remember, a unitary matrix has 3 angles and 6 phases. So in total, we have 9 angles because all the angles are broken and 17 phases. At the beginning, we have 18 phases, but one of the phases is a symmetry. A symmetry cannot be used to change bases because a symmetry phase means that in any basis, the term is the same, is invariant. So we have 9 angles, 17 phases. Okay. So we start off with 18 real parameters. Each Yukawa coupling has 9. And we have 9 angles we can remove. So in the end, we end up with 9 real parameters. imaginary parameters, there is only one, because we started with 18 imaginary and we have 17 phases, so we will have one imaginary parameter. So what are these 10 parameters? They are 3 masses for the charged leptons, 3 masses for neutrinos, and 3 angles in the PMNS and 1 phase in PMNS. Okay? So this way is easier. So if you have a model, you first figure out the global flavor group, what is when you don't have, and then you figure out the breaking, how the breaking works and what's left behind. Then you take the difference between the general number of flavor parameters and then broken generators. And that will be the number of physical parameters on which the processes will depend. Okay? Any questions about this?
Yes, Admir, I would have a question. Can you just go back 1 second? Okay. And what happens now? So when U3 cubed goes to U1L, then the masses get generated, right?
Right. So the breaking, yes. So when you have when you switch on Yukawas, then well, you don't have to think about electroweak symmetry breaking at this point. You should just think of the flavor symmetry. You really don't have to think about the electroweak symmetry breaking. So you just so you have the Lagrangian, and you first remove the Yukawa interactions. And without Yukawa interactions, you have the flavor symmetry, the big one, which is U3 cubed. And then you put in the Yukawa interactions, and then you see that it will break it down to the lepton number. Lepton number meaning the same phase to all the fields, and that one is still a symmetry. Mm-hmm. And then you see that you have nine angles and 17 phases, which correspond to the broken generators. So these are broken generators of the big global group. Broken transformations. And what does this mean? This means that you can use these broken generators because they are broken by the Yukawa interactions, meaning when you do a transformation, Yukawa matrix changes in a different base. When you go to a different, you do a transformation, it changes. So eventually you can go to a basis where you cancel some imaginary parameters in the Yukawa.
Yeah, right. So okay, I see.
So you take the general the number in the general basis, number of parameters, which is 18, and then you take the difference with the broken generators, and you get the number of physical parameters. Okay, so let's do the Majorana case. What is a Majorana case? Well, in Majorana case, we don't have a right-handed neutrino. But how then neutrinos get mass? Well, we have the Weinberg operator. Okay. Dimension 5 operator and some scale, which will give us, when the electroweak symmetry breaking happens, we will get a mass term for Majorana, mass matrix. But in this case, it's a bit different because the Majorana mass matrix is complex symmetric. In particular, yes. So it's a symmetric matrix, meaning that it's equal to it is equal to its transpose. How do we know it's symmetric? Because basically you have charge conjugation and the bar, the two cancel out. The property of the fermionic field. So if you have this fermionic field identity holds, psi bar chi is you flip them, and the chi charge conjugate psi charge conjugate. This fermionic field identity ensures that the Majorana mass matrix is symmetric. You can check this. Maybe you do it later on. All right. So the setup is a little bit different now. So we have one matrix which is complex arbitrary, the other one is complex symmetric, the Majorana mass matrix. Again, we can use the singular value decomposition. In fact, for the symmetric complex matrix, we do not need two different unitary rotations, only one. In particular, if MT equals M, then V and U are the same matrix up to a charge conjugate. So there is only one matrix needed to do the rotation to diagonal for the symmetric case. All right, so let's do these rotations in the broken phase. I'm doing the brute force way. Note here that I only have a single unitary matrix, U nu, to get the neutrino mass matrix. Okay. Again, the rotations cancel everywhere else except in the W interaction. Only here we have the effect of the rotations. So remember, now we can use the phases to remove some of the freedom in the PMNS. We have 3 real and 6 imaginary, and out of these 6 we can only remove 3. So we can use the phases of the charged leptons, but we cannot use neutrino phases. Why? Because if you look at the neutrino mass term, which is this one, if you do a phase, then you will spoil the sign of the mass term. So mass has to be real positive value. So if you do a phase, it will not be a symmetry of this term. Like for the charged lepton, if you do it for the charged leptons, nothing will change. But if you do it here, you change M. Okay, so you cannot use the phases of the neutrinos, only the charged leptons. And therefore, in this case, we have 3 angles and 3 phases. So if neutrino is Majorana, in addition to the one phase, Dirac phase, there are 2 additional CP violating phases. So that was a brute force counting. Let's do the group theory approach. Okay, now we have U3 square, U3L times U3E, because we don't have a right-handed neutrino. And this global symmetry is broken to 0. Even lepton number is violated, right? Because we have a Weinberg operator. With these 2 terms, even lepton number is violated. So how many parameters we have in a general basis? So we have 9 real for the electron Yukawa, we have 9 real and 9 imaginary. For the neutrino Yukawa, because it's a symmetric matrix, we have 6 real and 6 imaginary. And you can do, again, this trick. You can take the difference between the parameters in the general basis minus the number of broken generators. And if you do this trick, you will see that you have 9 real parameters and 3 imaginary parameters. So these are 6 masses, 3 mixing angles, and 3 phases. Okay. Okay, maybe in the last 12 minutes, I want to do the example of the vector-like top quark partner. So I will extend the standard model by adding a vector-like quark. In particular, this guy will be in the same representation. Both the left chiral and the right chiral field will be in the representation of the right-handed top quark, okay, which means that they are a weak singlet and hypercharged 2/3. So let's mix only with the top quark. What does it mean? So I will only have Q3L aligned to the top quark. I will put the CKM in the down sector. So how does the Lagrangian look like? In general, it has these 3 terms. Okay. So the first term is the usual Yukawa coupling. The second term is the interaction with the heavy right-handed top. And the last term is the mass term. This one. You can show that this is the most general Lagrangian. In fact, there is another term one could write down. You can see this is also gauge invariant. So because capital TL and TR in the same representation, but you can rotate this way before electroweak symmetry breaking. Maybe if you are going to do this exercise later on, you can convince yourself that you can use U2R. This is the global symmetry, flavor symmetry of the sector, to rotate away this term, to start with the basis when it's 0. So you only have 3 terms. Okay. Now let's do the electroweak symmetry breaking. Okay. And then you get the mass matrix. So this is the mass matrix. The right-handed fields in the column and the left-handed fields in the row. And then there is this matrix which has a 0 here. And it has these 3 terms. Now phenomenology tells us that the entry capital M, so this entry, is much bigger than the first 2. So we haven't found this guy at the LHC, and its limits are like 1 TeV compared to, let's say, top quark mass, which is 170 GeV. So there is an order of magnitude hierarchy between these terms. So let's use this and do diagonalization. So I want to diagonalize matrix A, B, and C, and there is the 0. And I have this hierarchy that A and B are much smaller than C. Okay, A and B are much smaller than C. So the first thing which I will do is this left-handed rotation. Okay, so I'll do the left-handed rotation. And then I will get this thing here. Now, remember that C is much bigger than B, which means that we can approximate cosine with 1 and sine with the angle, and therefore we can get so we want off diagonal term is 0. We want to diagonalize, so we get the sine is B over C. Okay. So, but we are not done yet because we have this term left. But we are in a similar situation. Now we have so these are triangular form matrices. So now we have we have to do the right-handed rotation. And this is what we get. And then we can get the right-handed mixing angle. Of course, this is only perturbative diagonalization. If you can keep on going to get finer corrections to this. Anyways, what we get out from this exercise is that the mixing angle, left-handed one, is the ratio of the off-diagonal Yukawa over the mass of the heavy guy. And the right-handed mixing is the left-handed mixing times the ratio of the top quark, the mass of the top quark to the top partner. So right-handed mixing is smaller than the left-handed mixing. Okay? So we can how do we go from interaction basis to the mass basis? So we are doing these rotations with the left-handed and the right-handed mixing angle. Okay, so let's calculate, for example, Higgs couplings, the Higgs-Feynman rules. Remember the initial Yukawa-Lagrangian? Now I write the flavor interaction, it was written in the interaction basis. Now I write it in terms of the mass basis. So I have to put these rotation matrices. The mass term will get diagonal. So this is just the procedure that I have done, that I've just done. So I found I expressed the left-handed and the right-handed mixing angle in terms of the parameters inside. So this will be diagonal. But the Higgs couplings will come from the fact that I replace the Webb with the Higgs. Okay. So now I have to do these rotations. I have to multiply the matrices to get the Higgs Lagrangian. And if you are going to repeat this, please be careful with these approximations. When you do the expansion in the angle, you have to be careful not to miss some terms which are of the same order. Okay. So in the end, what you get is this Lagrangian. So here you can see that the coupling of the Higgs to the top quark, to standard model top quark, is modified by this term, by the cosine square of the mixing angle. In addition to that, Higgs couples to the heavy guy by the sine square of the mixing angle. And also there are flavor violating couplings. For example, heavy top quark can decay into Higgs and the light top quark with this off-diagonal coupling. So you can see it here with this vertex Feynman rule. Okay. Another interesting consequence is that the production of the Higgs at LHC will not change a lot. So the dominant production mechanism is the gluon fusion. And in the gluon fusion, you have, in standard model, you have only the dominant contribution is the top quark. But now in this extended model, you have additional contribution from the heavy top quark. Now the coupling of the top quark is modified by cosine square, while the coupling of the heavy top, if you assume that mass does not matter, and I will prove this in the last slide. Let's assume for the value of this loop, the mass, if it's heavy enough, the mass doesn't matter. Then the only difference between the two is that one diagram goes with the cosine square and the other one with the sine square. So it's this sine square here, which goes in this. Okay. So then the rate for the gluon fusion will be standard model-like. This is a very interesting prediction in for example, these top partners from Composite Higgs, that they don't modify the rate for the gluon fusion a lot. So, okay, let me just tell you why the loop function doesn't depend on the mass when it's heavy enough. So let's look at this loop, but we will not compute it. We will use effective field theory. So this is the loop, the triangle between two gluons and the Higgs, and there is some heavy fermion psi running in the loop. It couples to the Higgs with the Yukawa psi. And we are going in the limit where the mass of psi is much bigger than the Higgs mass and the energy of the partonic center of mass energy. So let's just do naive dimensional analysis. we are contracting this to a point, to a local operator. Let's first write this operator. So this operator has the Higgs field, and it has two gluon fields, this one and that one, gluon field strength. Now you can do the counting of the canonical dimension of this operator is 5. It's a dimension 5 operator. What else should go in the Wilson coefficient? So we have two couplings of the two strong couplings, this one and that one. So this will be alpha strong over 4 pi. Alpha strong over 4 pi, meaning there is also a loop factor. Alpha strong is g square over 4 pi, so it's g square over 16 pi square. 16 pi square is the usual loop factor. And then there is also this Yukawa, which goes here. Okay. And what else? So now we know that Lagrangian has dimension 4. So we have to put some scale. Which scale? There is only one scale in the problem. We have to put m psi, right? 1 over m psi to match the dimension. So here you can really see the power of effective theory. Even without computing, we can get this. And there is order 1 loop, which comes from the computation of the loop. Okay. But what I want to show you here is that Higgs couples to heavy particle proportional to its mass, right? Now, if we plug in this, for example, here, then we will get that Wilson coefficient will be independent of the mass. So the coupling will cancel. The coupling will cancel, and the Wilson coefficient will be something which is just alpha strong over 4 pi v. Yeah. V is the web of the Higgs. That's it. So, which means if m psi goes to infinity, the Wilson coefficient doesn't depend on m psi. This is the example of non-decoupling. Non-decoupling is very strange in effective theory. So does this mean that the Higgs is sensitive to infinitely heavy particle in the loop? No, it doesn't mean this. It simply means that, as you increase the mass, this will hold, but at some point it will break because the coupling will go non-perturbative. And at that point, we cannot compute loops. But there will be a regime, in particular, in this example of the top quark and the heavy top, they are roughly in that regime. So the loop functions are the same. The only difference between the two loops is this cosine square and sine square. Any questions?
Admir, I would have just a quick question. So can you go back to the glue Higgs diagram?
Yes.
So how can we understand this 1 over m psi factor in maybe another way? So from the propagators inside of this loop, one would get something maybe roughly like 1 over m psi cubed. And then there is the Higgs coupling.
Which is m psi.
Which is m psi, yes.
And there is a chirality flip on one of the legs.
Aha, okay, so
take like this left. Higgs coupling is chirality flipping because it's a scalar interaction. You go right. Gluon coupling is chirality preserving. It's a vector interaction. Then you go right, and then again you hit a gluon. So to surpass this thing, you have to insert the top mass.
Ah, okay.
So you have the top mass times from the chirality flip, the top mass times from the Yukawa vertex, and over m top cube. And this is exactly 1 over m top.
Ah, okay, cool. Thank you.
Sure. All right, well, thank you all, and see you next week. Bye.
Thank you. Bye.
Bye.
Bye.